So we will see how to represent a cell on paper. Here the IUPAC steps to write a cell reaction and galvanic cell. Here represent the given galvanic cell with standard conventions. That means electrode on the left side of the representation shows that it is anode. On paper, when we represent any electrode, it is the anode, and oxidation takes place at this electrode. Then write half cell oxidation reaction and half cell reaction for it. This is the first step. Then the second step. The electrode on the right side of the representation shows that it is cathode, and reduction takes place at this electrode. Then write down the half cell reaction and reaction half cell for it. Then balance above two reactions for the electrodes for oxidation and reduction, and add the two reactions and obtain overall cell reaction. Here the represent the cell conventionally. Here step 1, the electrode, suppose Pb solid, it is in contact with Pb++ ions having concentration 1 molar. Here the salt bridge is represented by putting two vertical lines. This represents a salt bridge, and then this is the cathode. That means the cell which is represented at right hand side, and it is the cathode. Here Ag+ ions in aqueous medium having concentration 1 molar, oblique line, and this is a silver in a bracket yes. That means silver metal electrode, it is in contact with solution containing Ag++ ions. This is the representation of a cell. Then step 2, write left hand side half cell reaction. That means in this example Pb, it is on a left hand side and it shows the oxidation. Therefore the oxidation reaction, it is written like this. Pb, it dissolves and it gives Pb++ ions plus 2 electron. This is the oxidation step. Then right hand side half cell reaction. As we have here silver electrode, it is in contact with silver ions. This is our right hand electrode, and at right hand electrode reduction takes place. Therefore the reduction reaction at a right hand electrode, it is written as Ag+ in aqueous medium plus 1 electron minus, it gives Ag, that is the reduction reaction. Then the balance the electrons of above two half cells. Here multiplying equation number 2 by 2 so that we can have the number of electrons 2. Therefore when multiplied with this equation by 2, we get 2 Ag plus 2 electrons, it gives 2 Ag. Then adding equation number 1 and 3. Equation number, this is the equation number 1 and this one is the 3 equation. We get here Pb plus Ag plus in aqueous medium, it gives Pb2++, it is plus Ag. This is the overall cell reaction. Then here the steps to find EMF of a galvanic cell. Here represent the given galvanic cell with standard convention. Then electrode on left side of the representation shows that it is anode, and oxidation takes place at this electrode. Then the electrode on right hand side represent it is a cathode and reduction takes place at this electrode. Then next step, obtain standard oxidation potential value from the electromotive series for material of cathode and anode and use the formula for calculation of EMF of a cell. Here E0C it is equal to E0 cathode minus E0 anode, that is ER minus EL. We can find E0 of a cell by using the EMF from a standard series. Then suppose for example to find EMF of a Daniell cell. Here we know that the Daniell cell is represented as like this. Here ZnS oblique line, it is in contact with solution containing ZnSO4 in aqueous medium, and suppose the concentration here it is 1 molar. Then double vertical line, then CuSO4 concentration here 1 molar, it is in contact with copper electrode. This is our cathode and this one is our anode. Then E0Zn it is always minus 0.76 and E0Cu it is 34 reduction potentials, and here by using this equation we can find the E0 of cell it is equal to 1.1 volt. That means 0.76 minus 0.34, and this becomes minus plus, and we have this is the 1.1 volt. This is the potential of Daniell cell. Then we will see the Nernst theory of electrode potential. So let us begin with the concept of electrode potential according to Nernst. Here a single electrode or half cell or electrode couple is produced when a metal is dipped in solution of its own ions. A single electrode or half cell or electrode couple is produced when metal is dipped in a solution of its own ions. For example, if we dip copper metal in a copper sulfate solution or zinc metal in a zinc, zinc sulfate solution, then a single vertical line here indicates a physical contact between the metal and its ions. Sometimes a couple is produced from gas and a solution of its ions. In such cases, noble metal like platinum is used as a conductor to absorb the gas. Then the concept of electrode potential. Here, Nernst in 1889 gave this theory of electrode potential. An electrode is a couple of active element and its ionic solution. When metal is immersed in its salt solution, it shows two opposite tendencies called de-electronation, that is oxidation, and electronation, that is reduction. Remember, oxidation means loss of electron. It is also called as de-electronation, and electronation means gain of electron. It is called as reduction. Then metals have a tendency to pass into solution as cation and liberate electrons. This process is oxidation or de-electronation. The tendency of metal to pass into its solution in the form of cations liberating electrons is called the solution pressure of metal, and it is represented as Ps. There is a reverse tendency of cation to deposit on an electrode by taking electrons, and this process is called as electronation or reduction. The tendency of ions in the solution to be deposited back on the surface of the metal by taking electron is called an osmotic pressure of ions, and it is represented by P0. Then the Nernst suggested the mechanism of establishment of difference of potential in a cell. This theory is based on the theory of electrolytic dissociation, and his idea of solution pressure and formation of the electrical double layer. Here, de-electronation, the process in which an atom or ion of an element loses one or more electrons, is called as de-electronation, and de-electronation takes place at the electrode when solution pressure of metal is greater than its osmotic pressure, and it is represented like this. Here the solution pressure, it is greater than osmotic pressure. The electrons released in oxidation are accumulated on the electrode. Here negative signs means a negative potential is developed on the metal, and on the other hand, solution acquires excess positive charge. Here solution, it acquires excess positive charge because of excess of cations. This gives rise to the electrical double layer at the electrode surface. Because of this electrical double layer, a potential difference is set up. As this potential is due to oxidation, it is called as oxidation potential. Here simply remember that this is the solution, any solution, and in that solution we have dipped any metal. Then what happens? Due to solution pressure property, this metal, it loses electrons and passes into the solution, and in the solution there is a formation of positive charge, and on the metal there remains electrons, and this is the formation of electrical double layer. Then for example, in Daniel cell, solution pressure of zinc is more. Zinc passes into its ion solution as Zn++ ions, and electrons released in oxidation get accumulated on the zinc rod. Thus, de-electronation takes place at the half cell in Daniel. Thus, we can write this is the reaction, oxidation reaction taking place at zinc. Zn it gives Zn++ ions plus 2 electrons. Thus, at zinc, a negative potential is developed which is due to the oxidation. Then the electronation, that is reduction. Here, the process in which an atom or ion of an element gains one or more electrons is called electronation. Electronation takes place at the electrode when osmotic pressure of metal is greater. Here, the process is reverse of the first. On the metal, there is a positive charge, and in the solution, there is a negative charge. And remember, here the osmotic pressure PO, it is greater than solution pressure. That means PS. And due to electronation, the electrode loss electrons continuously and acquires a positive charge, and the solution on the other hand acquires excess negative charge. Thus, electrical double layer is set up across the surface of the metal. Because of the electrical double layer, potential difference is set up as this potential is due to reduction. It is called as reduction potential. Remember, when a reduction potential occurs, the condition is P0 is greater than PS. For example, in Daniell cell, osmotic pressure of copper is more. Therefore, Cu++ ions from solution take electrons and deposited on the surface of metal. Thus, due to reduction, there is a removal of electrons from the metal surface, and electronation takes place at copper half cell in the Daniell cell. And the reduction reaction is Cu++ in aqueous medium. These ions take 2 electrons and there is a reduction of Cu++ ions, that is formation of copper. Thus, the copper electrode, a positive potential is developed due to reduction reaction. And the rate of electronation or de-electronation differs from metal to metal. Then there are three possibilities. Here, when PS is greater than P0, the solution pressure is greater than the osmotic pressure. The rate of de-electronation is greater than rate of electronation. The electrode undergoes oxidation and thus potential develops on the electrode and it acts as a anode. Then the second situation, when P0 it is greater than PS, that is when osmotic pressure is greater than the solution pressure, the rate of electronation is greater than the rate of de-electronation. The electrode undergoes a reduction, thus the positive potential develops on the electrode and it acts as a cathode. And when PS it is equal to P0, that is osmotic pressure equal to solution pressure. When the solution pressure is equal to osmotic pressure, the rate of electronation is equal to the rate of de-electronation. Thus, there is no double layer formation and hence no potential is developed on the electrode. Such an electrode is called as null electrode. Then, as we have seen in the last lecture, the Nernst equation. Here, for single electrode potential, let M be our metal and N be the number of electrons involved in the electrode. Then the reactions are M raised to N plus plus Ne minus. This is the oxidation reaction. And when we write this as M raised to N plus Ne minus, it gives M. This is the reduced reaction. And we can write according to Nernst equation at 25 degrees centigrade, E it is equal to E0 minus 2.303 RT by NF into log oxidation reaction and reduced reaction, and this is the EMF equation here. Okay, we will see the next point for tomorrow.